This is our last video in the chapter about liquids and solids and intermolecular forces. It is about phase diagrams. So we're going to go over the anatomy of a phase diagram, the basic parts that you should be able to identify, and we'll talk about the phase diagram for water and how super special and different and unique it is. So the anatomy of a phase diagram. We need to indicate where the solid, the liquid, and the gas would exist. So it's a similar looking graph to the one that we use to talk about vapor pressure and boiling point. It's going to be a pressure on the Y and a temperature on the X. And before we even show what a real phase diagram looks like, I bet we can make a fairly good guess. So if I had to guess purely based on temperature, where these different phases would fall, I would predict that the solid would have the lowest temperature, that the liquid would have the next lowest temperature, and that a gas would have the highest temperature. So I would predict that the diagram would look something like this. What about if you had to make a prediction based on pressure? Because of course you won't always have the phase diagram on hand and you have to remember how it looks. So if I were going to make a prediction based on pressure, I would think that gases tend to exist at pretty low pressures, and as you start to compress them and push them together and squeeze them closer and closer to each other, you end up with condensed phases, like solid and liquid. So I would predict that at low pressure, I would have a gas, and if I increase the pressure, I would end up with solid and liquid up here. Now, this is obviously not a real phase diagram, but sometimes you need a device to help you understand why the diagram looks the way it does. And if you were to add this temperature graph to this pressure graph, you would actually get something that looks a lot like a real phase diagram. Let's check it out. Okay, so here is a real phase diagram, complete with reflection of the dot cam. So just like we predicted, here at the low temperature is the solid, the mid-level temperature is the liquid, and at high temperature is our gas. And just like we predicted about pressure, the gas is here at the low temperature, and solid and liquid are at high pressure. Excuse me, gas at low pressure, solid and liquid at high pressure. So we have our solid is on the top left, gas on the bottom right, and liquid in whatever space is left. So you will need to be able to label where these are in the picture. We also can include the phase changes. So remember when we drew this curve? We drew this curve in the last video. This was our boiling point curve. And we learned about how boiling point wasn't just a point, it was a whole curve. It was a series of temperature pressure combinations. And we can do the same thing for other phase changes. So here's vaporization going from the liquid box into the gas box. Here's condensation going from the gas box into the liquid box. So we can do the same for the other transitions. So if we're going from solid to liquid, melting is going across this line, and freezing going across in the other direction. So this is like the melting point line. Is here. And then for our unusual compounds, solid to gas transition, sublimation is going from the solid area to the gas area, and deposition from the gas to the solid. So this is our sublimation point line. And notice that the way that we're making these transitions, the way I'm drawing these arrows, they're horizontal flat lines. So I'm picking a particular pressure and I'm changing the temperature to see what happens. If we wanted to, we could also draw a constant temperature line. We could say, what if we have something at a particular temperature? What would happen if we change the pressure? and we could draw a pressure transition, changing the pressure to change the phase in that way. So if I was at this temperature, whatever temperature this is, if I increase the pressure, I would compress a gas over the boiling point line into a liquid. So this is what we're going to use these diagrams for. We're going to have numbers along each axis. We're going to be saying, if I had a particular pressure temperature, what phase would it be in? Or if I had a gas at a particular temperature, what pressure might it be at? So the main points of the diagram that we have here, we have our solid, liquid, and gas phases. We have our phase transition lines. And there's a couple of other points that are labeled that I want to point out. So this point right here, I sort of wrote over it, but you can see it's called the triple point. So the triple point is where all three phases coexist at some temperature and pressure. So at this particular temperature and this particular pressure, gas, liquid, and solid all exist at the same time. Our other interesting point is up here, the critical point. Critical point is the highest temperature where a liquid can exist. So if we have a compound and it is a gas and we continue to increase the temperature and we move steadily to the right, once we reach this temperature, the critical point temperature, you reach sort of a no man's land of the phase diagram over here. And this is where you have a supercritical fluid. And a supercritical fluid has some properties of a liquid and some properties of a gas. It flows just like a liquid and a gas, and it has a density somewhere in between the two. So those are points you should be able to identify on our list here. So phases, transitions, critical point, and triple point. So those are points you should be able to identify if given any phase diagram for any compound, and with that information, you can use it to gain information. So now I want to look a little bit more closely at the phase diagram for water. All right, so here's our phase diagram for water, and we can see it's looking approximately the same. So here's the solid in the top left, here's the gas in the bottom right, and the liquid is the rest of the phase in the middle. The point that I want to draw your attention to is the melting point line right here. So if you look at the slope of this line, you can see there is a negative slope. Right, that line is pointing slightly to the left. And if we look at the same line up here on the quote unquote normal phase diagram, that line has a positive slope. Now this may not seem like a huge difference, but I can assure you that it is. It's a very important one. So let's think about what the significance of the slope difference of this line is. So this slope difference is about density. So this means that solid water is less dense than liquid water. And you might imagine that based on all the drawings we've made about hydrogen bonding and about the particular structure and way that water molecules like to line up so that they can get hydrogen bonding to as many possible hydrogens as they can. And so when you have solid water or ice, the molecules can't get too close together because they want to have the perfect angle to get the maximum possible hydrogen bonding. So the density of ice ends up being low density, whereas the density of liquid water is more dense because these molecules are kind of just jumbled together. So the density is higher. And the density is reflected in what happens to the material when you increase the pressure. So if I were to pick a point here in the solid and I increased the pressure by moving vertically, I would actually move over the melting point line and I would move into the liquid area. This is supposed to be a vertical line just for the record. If we were over here in the normal phase diagram, if I had a solid and I increased the pressure, I would never intersect that melting point line. I would continue to be a solid to the highest possible pressure. Whereas for water, if I increase the pressure, ice would actually end up melting to a liquid. And this feature of water is the reason life exists on Earth. So if the density of water was more dense than liquid water, like it is for most other compounds, then when water would freeze at the top of the ocean, a giant heavy chunk of ice would sink all the way to the bottom of the ocean and kill everything in the ocean every winter. And life may never have made it out of the ocean if it was killed off annually once a year. But because ice is less dense, ice floats on the top of water. Life is able to live underneath that top frozen layer if it ever happens. And that is why we have life on Earth. Thank you for coming to my TED Talk. But in all seriousness, the slope of the water line is a unique feature of this diagram, and that's what makes it, its special hydrogen bonding is reflected here in that diagram. So that is the end of the liquids and solids chapter and intermolecular forces.